Have you ever stopped to wonder what's really going on inside the maze of pipes under our cities? Or how does a massive 100-ton airplane just hang in the air? Well, it turns out the answer to both lies in the invisible world of fluid dynamics. And today, we're going to pull back the curtain on one single elegant principle that connects it all.
Right, so think about it. Our entire world runs on this hidden network of pipes. But how on earth do you measure the speed of something you literally can't see? It sounds impossible, right? But engineers found a super clever way to do it, and that's the puzzle we're going to solve together today. So, let's start with the challenge itself, what we're calling the invisible flow problem. How do you put a number on something you can't lay your eyes on? Well, the solution isn't about getting a better flashlight. It's about thinking about the problem in a totally different way. And here's the secret. The big breakthrough comes when we stop trying to see the flow and we start thinking about its energy. Believe it or not, energy is the key that's going to unlock this whole mystery for us. Okay, so let's dive into this idea of hidden energy. It turns out that any little drop of fluid moving through a pipe is carrying energy in 3 different forms. And if we can get a handle on these 3, we can understand the entire system. It's that simple. First up, we've got potential energy. Engineers have a fancier name for it. They call it elevation head. The easiest way to think about this is to picture a giant dam. The higher the water is piled up behind that wall, the more potential energy it has, just waiting to be unleashed. We represent this height with the letter Z. Then, of course, there's kinetic energy, or velocity head. This one's pretty intuitive. It's the energy of movement. You know, a raging river has a way more kinetic energy than a calm little pond. The faster the fluid is moving, the more of this energy it's got. The formula for it is v squared over 2g, where v is just the velocity. And finally, the third piece of our puzzle is pressure energy, or pressure head. For this one, imagine you're squeezing a water balloon. That pressure you're putting on it, that's storing energy inside the water. That's pressure energy. And we represent that with P for pressure, divided by gamma, which is basically a measure of the fluid's weight. So here's the big takeaway. The fluid's total energy, what we call the total energy head, is just the sum of these 3 parts. It's like an energy bank account with 3 subaccounts: potential, kinetic, and pressure. And here's the crucial part we're about to see. That total balance doesn't change. And this leads us directly to a massive breakthrough from a physicist named Daniel Bernoulli. He had this incredible insight based on the fundamental law that energy can't be created or destroyed. He realized that the total energy in a moving fluid has to stay constant. And that simple idea, well, it changed everything. And here it is in all its glory. Bernoulli's equation. Now I know, it might look a little intimidating with all the letters and symbols, but all it's really saying is that if you add up the pressure energy, the kinetic energy, and the potential energy at any point along a fluid's journey, the grand total is always going to be the same. It's a perfect balancing act. Let's put it even more simply. The fluid has a fixed energy budget. That's it. It can shuffle energy between its 3 accounts. It can trade some pressure for some speed or some height for some pressure, but the total amount of energy in the system always stays the same. Now this is the most important consequence of Bernoulli's principle. Because that total energy is constant, if you make one type of energy go up, another one has to come down. And the most famous trade-off, the one that explains so much, is this. When a fluid speeds up, its pressure drops. More speed, less pressure. That's the golden rule right there. Okay, now for the fine print. Bernoulli's equation is a bit of a perfectionist. It works perfectly for an ideal fluid, one that isn't sticky or viscous, flows nice and smooth, and can't be compressed. Of course, real-world fluids are a little bit messier, but this principle is still an unbelievably powerful tool for getting us really close. So theory is great, but how does this amazing principle actually help us solve our original problem? Well, this is the payoff. Let's look at a few ingenious devices that put Bernoulli's principle to work. The Venturimeter is just a brilliant example. So look at step 1. Fluid comes in through a nice wide section of pipe. It's moving slow, its pressure is high. But then look what happens. We squeeze it into this narrow throat. To get through, the fluid has no choice but to speed up, a lot. And what did we just learn? When velocity goes up, pressure goes down. And bingo! By measuring that predictable drop in pressure, we can calculate exactly how fast the fluid is moving. We've made the invisible visible. But that's not the only trick up our sleeve. There's another incredibly clever device that uses the same principle, just in a slightly different way. It's called the pitot tube. And if you've ever looked closely at the outside of an airplane, you've definitely seen one. The idea behind a pitot tube is just genius in its simplicity. It's basically a hollow tube pointed straight into the flow. The fluid, or in an airplane's case, the air, rushes in and then slams to a complete stop right at the sensor. At that exact point, all of its kinetic energy, its energy of motion, gets converted into pressure energy. And by measuring that spike in pressure, we can figure out exactly how fast the plane was flying. So measuring energy is one thing, but to really get a gut feeling for what's happening along an entire pipe, engineers came up with a way to visualize it. Let's take a look at how you can actually draw a picture of a fluid's energy. First, we have something called the hydraulic grade line, or HGL. Just think of this line as showing us the combined potential and pressure energy at any point. The easiest way to picture it is if you could stick a tiny open-topped straw into the pipe. The HGL is the level the water would rise up to inside that straw. Then, floating above the HGL, we have the energy line, or EL. This one's simple. It represents the total energy, potential, pressure, and kinetic all added together. And because we know the total energy for an ideal fluid is constant, this line is perfectly flat and perfectly horizontal. It's our energy ceiling. Now, here's where it all clicks together. The magic is in the relationship between these two lines. That vertical gap, the space between the flat energy line on top and the fluctuating hydraulic grade line below, that gap is a direct visual measurement of the fluid's kinetic energy. So if the gap is wide, it means the fluid is moving fast. If the gap is narrow, it's moving slow. It's like having a speedometer for the entire length of the pipe. So there you have it. We started with a simple question about hidden pipes and ended up with a fundamental principle of the universe. Now that you understand this amazing trade-off between pressure and velocity, you're going to start seeing it absolutely everywhere, from the way a baseball curves to how a race car sticks to the track. It's one of those truly invisible forces that shapes our entire world.